Assalamu alaikum dear students. I welcome you to 39th lecture of probability and stochastic processes. In recent lectures, we have been analyzing Markov chains, which are collection of random variables with interdependence, usually described in terms of transition probabilities. These transition probabilities are conditional probabilities of a previous random variable knowingly taking a certain value and then assigning probabilities to jumps to different values of next random variable. So far, we have restricted our analysis to those Markov chains which have only a finite state space. By state space, we mean the finite set of values that this collection of random variables can assume. We usually label these states 0, 1, 2, 3, 4. You may also label them by numbers like 1, 2, 3, 4. It's up to you. So we have a finite state space, a finite collection of values, labeled values with integers, which this collection of random variables can assume. And we have an infinite collection of these random variables, and these random variables are all indexed. They have a precedence. They are well ordered. And we talk about relationship of nth random variable with n plus first random variable in terms of the transition probabilities of going from a certain value at index n to a certain value at index n plus 1. In this type of one-step transition probabilities, we use a stochastic matrix which tabulates all possible one-step transitions from states of nth random variable to states of n plus first random variable. We also talked about n-step transition probability matrices, where those matrices tabulate possible transitions and their probabilities in n steps from a certain state of random variable with index m and the next random variable with index m plus n. So if the jump is of size n, we are talking about n-step transition probability matrices. By working with these one-step transition probability matrix and n-step transition probability matrix, we can analyze the behavior, the evolution of a Markov chain as different random variables take on their values when their index time comes around. We are usually interested in long-term or asymptotic behavior of Markov chain in terms of long-term stationary probability distribution. That is, in the long run, what's the probability that a random variable with very large sampling index, with very large sampling instance, has probability of exhibiting a certain state with a certain probability. So we are interested in finding the probabilities of a long-term random variable having different states as the outcomes of that experiment which is performed to get the values of that random variable. So these one-step and n-step transition probability matrices were used to define one simple concept, that was n-step reachability. We were interested in the idea of being able to reach from a certain starting state, say I, to a certain destination state, say j, in n steps. And if we want to find if there is a positive probability of this type of transition happening, we just look at I, j entry of n-step transition probability matrix. If that entry is non-zero, it's positive, then there is a positive probability that when this collection of random variable evolves, when this Markov chain evolves, we can jump from state I to state j in n steps. By defining these type of one-step and n-step reachability, we talked about the importance of observing an n-step transition probability matrix which has all entries non-zero. These entries are conditional probabilities, so they are either 0 or a number between 0 and 1. So if all the entries are between 0 and 1, actually more than 0, then this type of transition probability matrix indicates that in certain number of steps, it's possible to jump from any state to any state. If all the entries are positive numbers greater than 0, then we have a positive non-zero probability of starting from any state and reaching any state in that number of steps. So if we have a finite state Markov chain and we are given its one-step transition probability matrix, and we try to find its n-step transition probability matrices for different values n, and we get an n-step transition probability matrix which has all entries which are greater than 0, then this type of Markov chain is called a recurrent Markov chain. In a recurrent Markov chain, all states are visited infinitely often because we have an infinite collection of random variables, because there are countably infinite sampling instances where these random variables assume their values, and while this Markov chain is evolving, each state is visited infinitely often because that is mandated by all entries of an n-step transition probability matrix being greater than 0. If all these entries are greater than 0, then conditional probabilities of moving from a certain state to another state in n steps is also non-zero. Then probability is greater than 0 that the destination state will be visited, provided that the starting state is given. And if this is true for all the states, then all states are visited infinitely often, and we call this type of Markov chain a recurrent Markov chain. And those states which exhibit this type of behavior, those states which are visited infinitely often, are called recurrent states. Another implication of having an n-step transition probability matrix with all entries greater than 0 was that such Markov chains have a unique long-term stationary probability distribution. That is, for this type of Markov chain, it doesn't matter which condition is the starting condition, what is the probability distribution of the first random variable. In the long run, the long-term random variable is going to have a certain probability distribution which is unique and it is invariant. When I say it is invariant, it means that at nth step and n plus first step, the probability distributions are same, because after that, in the long run, when the n is large, the probability distribution of those long run random variables do not change. This is shown in the slide that you will see now, and in that slide it says that pi with an index n plus 1, that is probability distribution at sampling instance n plus 1, is equal to the previous probability distribution pi n multiplied by p, where p is one-step transition probability matrix. So if this Markov chain has a stationary probability distribution and it has reached there, then in the long run, this probability distribution pi n plus 1 is same as pi n. When you use this fact and assume that the long-term probability distribution is pi, then this equation turns into an equation which is pi times p is equal to pi. That means if you have a stationary probability distribution pi and you take this as a row vector and multiply it with p, the one-step transition probability matrix, you will again get the same row vector pi, which is the stationary probability distribution. If you look carefully at this equation, it says that pi is a left side type eigenvector in terms of eigenvectors and eigenvalues for a square matrix like P. if we multiply P with a certain vector and get the same vector back or its scaled multiple, then we call this vector to be the eigenvector, and that scaling factor is called eigenvalue. In this particular case, that eigenvalue is 1. When you take this pi times P, you again get pi. So pi is the eigenvector and 1 is correspondingly eigenvalue. So if we have a finite state Markov chain and it has a unique stationary probability distribution, that probability distribution can be interpreted as an eigenvector of one-step transition probability matrix P. The eigenvector is the values, all the values that we assign to probabilities to different states put in a row vector. In last lecture, I asked you to use MATLAB to do this eigenanalysis. And I told you that by default, MATLAB uses right-sided column type eigenvectors when you ask it to do the eigenanalysis. But in our particular case, we are using left-sided row type eigenvectors. Today I thought I should present such an analysis for a few simple cases so that you know how to handle these left-sided row type eigenvectors versus right-sided column type eigenvectors. So let's apply this eigenanalysis using MATLAB on simple cases that we analyzed in the last lecture. The first case that I'm going to describe to you through this eigenanalysis is the case of three-state Markov chain representing an electronic device, a machine, which sometime breaks down and then it gets repaired either locally or in a specialized repair facility. Let's have a quick look at this simple Markov chain, its transition probability matrix, and its infinite power, infinite step transition probability matrix, which is the value to which these n-step transition probability matrices converge. You can see on your screen that for this Markov chain, we have a very simple 3x3 one-step transition probability matrix, which does not have all entries as non-zero. Some entries are 0. But if you take two-step transition probability matrix, then this matrix has all entries greater than 0. So this Markov chain is a recurrent Markov chain, and it is possible to visit all states from all other states. And if you continue to take higher and higher powers of this one-step transition probability matrix, you will converge to this matrix, which is P infinity, and it has all rows which are same, and these rows are actually pi, the long-term stationary probability distribution. So for this Markov chain, long-term stationary probability distribution is 0.043 for state 0, 0.087 for state 1, and 0.87 for state 2. Before doing the left-sided row type eigenvector-based eigenanalysis of this case, let's have a look at the traditional right-sided column type eigenvector-based eigenanalysis. The next slide shows how you perform a regular traditional eigenanalysis of a square matrix P when you have your vectors as right-sided column vectors. So we have P as our square matrix, and if X is an eigenvector of this square matrix, then we say P times X, we multiply this square matrix with this column vector, and we get that same column vector scaled by lambda. So this lambda is eigenvalue and X is eigenvector. Since this lambda is a constant, just a number, you can put it on the left or on the right. I have put it on the right to emphasize the way you expand this equation to transform it into a matrix type equation. Suppose we have this matrix P as a 3x3 matrix. in that case there will be 3 eigenvectors with corresponding 3 eigenvalues. The next line shows that if you have XA, XB and XC as 3 column vectors being 3 eigenvectors, then you can put these 3 column vectors side by side and you will get a square 3 by 3 matrix. This matrix is shown in expanded form on the line below. So on the upper line, XA represents a 3 by 1 column matrix or column vector. Similarly, XB is also a 3 by 1 column vector and XC is also 3 by 1 column vector. So if you multiply P with all these eigenvectors which are column vector, you will get lambda A times XA, lambda B times XB and lambda C times XC. And if you expand these column vectors again and write them in a matrix multiplication form, you will have this matrix with XA, the 3 entries of XA being the first column, 3 entries of XB being the second column, and 3 entries of XC being the third column. So this is a matrix which gets multiplied with a diagonal matrix which consists of only eigenvalues. The top left eigenvalue is YA, lambda A, the middle eigenvalue is lambda B, and the lower right eigenvalue is lambda C. Now you should understand why I put lambda times X and X times lambda on the top line, because this is closer to this X times lambda. All the column vectors which are eigenvectors are put together in this matrix, and that happens to be on the left, and the diagonal matrix consisting of all 3 eigenvalues in the main diagonal happens to be on right. If you switch the location of these 2 matrices, this equation does not hold. Hence, we have to put the diagonal matrix of eigenvalues on the right. If we represent this matrix of 3 eigenvectors with V and this diagonal matrix of 3 eigenvalues with D, then this whole matrix multiplication equation becomes PV is equal to V times D. So it's important to observe this, that if we are using the right-sided column type eigenvectors and we put 3 column vectors side by side to form this square matrix, then the equation relating P and this matrix and the diagonal matrix happens to have V closer to the equality. So in this equation, V is next to equality sign on the left and also on the right. So if we remember this, it will be easier for you to distinguish between left-sided eigenanalysis and right-sided eigenanalysis. Starting with this equation which describes the matrix multiplication version of the above equation, PV being equal to VD, we can get 2 representations of D, where D is V inverse times P times V and P is V times D times V inverse. So P, the starting matrix that we have, can be expressed as V times D times V inverse. This expression is only valid for right-sided column type eigenvector based eigenanalysis. For other eigenanalysis, the expression for representation of P is going to be different. Let's have a look at that type of eigenanalysis where X is a row vector, P is the same square matrix, and we say that we multiply X with P where X is on the left, a row vector. So X times P is lambda times X. X is eigenvector, a left side type, row type eigenvector. If we expand this equation and actually write the values of, say, one of the 3 eigenvectors that we can use, XA, then this equation expands to this row vector, which is this X with 3 entries, XA1, XA2 and XA3, this row vector gets multiplied with P, the square matrix, and you get lambda A times this row vector xa1, xa2, xa3. If we have three eigenvectors, all rows, we can put them one above the other with xa on top, xb in the middle, and xc below, and take this 3 by 3 square matrix and multiply it with P. We have an equivalent representation which is based on this upper equation that says if we have such a 3 by 3 matrix which consists of 3 rows of row type eigenvectors and multiply it with P, which is equivalent to multiplication of a diagonal matrix which has all 3 eigenvalues in the main diagonal times the same 3 by 3 matrix which has 3 eigenvectors as 3 rows. A compact representation of this matrix multiplication is V times P is equal to D times V. This is different compared to the right side eigenanalysis. In that case, V was closer to equality on the left as well as on the right side. But here V is far away from equality both on left and on the right side. So this is the difference. If you remember this difference, you can distinguish between left-sided and right-sided eigenanalysis. So if we start with this matrix multiplication Vp is equal to dV, you can have two representations showing the value of D and P in terms of other matrices, and D is V times P times V inverse, and P is V inverse times D times V. So order of inverse and regular V have been switched. Furthermore, in the case of right-handed eigenanalysis, this vector V was column vectors put side by side. In case of left-handed eigenanalysis, this vector, this matrix V is rows. The eigenvectors being represented as rows, rows put one above the other. I hope it's clear to you now how you perform left-sided eigenanalysis using rows as eigenvectors and how you perform right-sided eigenanalysis with columns being the eigenvectors. Let's have a look at application of this method on finding the higher powers of P, where P is our one-step transition probability matrix. And we know that we use this one-step transition probability matrix to find n-step transition probability matrices by taking nth power of this P. So let's have a look at a slide which shows that you can find this higher power of P very simply by representing this P in terms of V inverse dV, where V is a matrix which is all rows of these eigenvectors put one above the other. The details of this equation have been shown to you just a minute or two ago. So if you have a representation of P like this and you want to take its higher powers, you just write this expression V inverse d V next to it and again next to it, and keep on writing these things and keep on multiplying. So if you keep on writing these expressions side by side, you will see that V and V inverse will be next to each other. So when you multiply V and V inverse, it gives you an identity matrix, and that does not play any role in the multiplication. So eventually you will end up with a V inverse on the left, a D raised to power n in the middle, and a V, the last V, on the right. So P raised to power n is nothing but V inverse times D raised to power n times V, where D raised to power n is nth power of a diagonal matrix with eigenvalues of this matrix P on the main diagonal. So if you take higher power of this diagonal matrix, you take higher powers of individual eigenvalues, which are shown on the main diagonal of this D raised to power n matrix. all this empty space above and below main diagonal represents entries which are all 0. The slide that you just saw is very similar to the slide that I showed you in the last lecture. And I reproduced this slide along with all the ideas that are needed to understand that slide so that you can understand all these eigenanalysis based ideas very clearly. I hope you are clear about these ideas of left-sided eigenanalysis and right-sided eigenanalysis and how you take higher powers of P using this diagonalization. Let's apply this diagonalization procedure on that simple example of three-state Markov chain of that device which gets repaired locally or in a specialized facility. The next slide shows you the same example where we have that Markov chain, it's P and it's P infinity or P raised to power infinity, which is the destination of the convergence of all this sequence of n-step transition probability matrices. If we take this P and apply diagonalization using the right-sided eigenanalysis, even though we are supposed to apply the left-sided eigenanalysis, but I will start with the traditional right-sided column type eigenvectors based eigenanalysis. So if we take that P, and I have written this P infinity for reference on your slide so that you know to which value this is going to converge or it is supposed to converge. So if we perform the right-sided eigenanalysis, you get a V, which is 3 column vectors which are eigenvectors of this matrix P. And this is D, the diagonal matrix containing all the eigenvalues. So 3 eigenvalues are 1, 0.57 and minus 0.7. And corresponding eigenvectors are shown as 3 columns. So eigenvector corresponding to eigenvalue of 1 is 0.58, 0.58 and 0.58. You can clearly see that none of these column vectors in V have any resemblance to these rows which represent the stationary probability distribution for this recurrent Markov chain. One big reason is that we use the wrong type of eigenanalysis. We use the right-sided eigenanalysis where we should have used the left-sided eigenanalysis. Hence, there is no resemblance between these rows which represent asymptotic probability distribution and the 3 columns. One important thing to note is that in these columns, some entries are positive and some are negative. So we cannot have these columns as stationary probability distributions. We might have this, but this is not going to be the case, as it will be obvious as we study this eigenanalysis. Let's apply the proper left-sided row types eigenvector based eigenanalysis to this problem. And if we do that, we get our diagonal matrix D, which has the same 3 eigenvalues in the main diagonal, and we get a matrix V. And in this matrix, the rows are eigenvectors, and corresponding to eigenvalue of 1, the eigenvector, the top row has entries which are minus 0.05, minus 0.099 and minus 0.99. And corresponding to other 2 eigenvalues, we have 2 other eigenvectors shown as middle row and the bottom row. If you are wondering why we are not getting any of these rows as this row in that convergent destination matrix, then you should think about the eigenvalues and eigenanalysis. Corresponding to an eigenvalue of 1, MATLAB gives you this eigenvector, which means that if you multiply this row vector with the given matrix P, you are going to get the same row vector. Similarly, if you take a scaled version of this row vector and multiply that with P, you are going to get the scaled version of that row vector. So it doesn't matter what vector, as long as it is a scaled version of this vector is used for matrix multiplication, you will get the same row vector back. So we are free to use any scale constant to multiply all the terms for scaling up, or dividing with the scaling factor to make these terms smaller. We can even use a negative scaling vector to get all values that will be positive. So I think if we pick a proper scaling factor, we can have this row which is corresponding to an eigenvalue of 1 equal to these rows which are shown in P infinity. So how do you pick that scaling factor? You just sum all these entries and you get a number. You divide every item in this row with that number. The reason is that these rows are probability distributions and they should sum up to positive 1. So if we take that sum of three negative numbers, it comes out to be 1.412 or something. And if you divide only the top row with that number, you get this new row, which is again an eigenvector corresponding to eigenvalue 1, and this is exactly equal to this row vector, which is the stationary non-variant probability distribution of this simple recurrent Markov chain. I hope this process of diagonalization and finding the higher powers of matrix P through diagonalization was clear to you. I used MATLAB again to find these eigenvectors and eigenvalues, but because MATLAB uses by default the right-sided eigenvectors, I had to transpose my probability matrix P, the one-step transition probability matrix P, and then I took the eigenanalysis of that transposed matrix, and it gave me a diagonal matrix D and a matrix V, which were columns. But on this slide that you just saw, I rotated that also. I transposed that also to show those eigenvectors as rows. The proper method is to use left-sided eigenanalysis, but if you want to use MATLAB to do all the computations, you take transpose of one-step transition probability matrix before you call MATLAB through the command EIG for eigenanalysis. Let's apply this eigenanalysis procedure to the next example, which is 4-state random walk with perfect reflection. We have talked about this Markov chain in the previous lecture, so let's quickly go to that Markov chain and its eigenanalysis. You can see on the slide that this Markov chain is represented by a 4x4 transition probability matrix, and if you do the proper eigenanalysis on that 4x4 one-step transition probability matrix, you get two matrices. One is D, which is a diagonal matrix with eigenvalues on the main diagonal, and that has 1, -1, +0.5 and -0.5. So as you take higher and higher powers of this diagonal matrix, you are going to get 1 in the top left corner always. But in this location 2, 2, you are going to get either 1 or -1 depending upon the power. If you are taking even power, you will get +1, and if you take odd powers of D, you will get -1 here. And these numbers 0.5 and -0.5, they will converge to 0 because their magnitude is less than 1. So you will get a matrix D and corresponding matrix V, which is a matrix of 4 eigenvectors shown as 4 rows, one above the other, has this form, where corresponding to eigenvalue 1, we have an eigenvector of 0.31, 0.63, 0.63, and 0.31. And corresponding to eigenvalue of -1, the eigenvector is almost same, with only difference being that two entries have negative sign in front of them. And this P is the one-step transition probability matrix that was used in this diagonalization. So if you look at this V, this top row could be used for long-term probability distribution, but we should not call that long-term transition probability matrix, because you can clearly see that there are two eigenvalues with magnitude equal to 1. So this Markov chain is not going to have a unique long-term stationary probability distribution. It's going to switch between two probability distributions depending upon the sampling instance. If the sampling instance is even, you will have one probability distribution, and if the sampling instance is odd, you will have another probability distribution. Let's try to find the high powers of this one-step transition probability matrix P through this diagonalization. As it was shown to you a few minutes ago, that P raised to power n is equal to V inverse times D raised to power n times V. So if you take very high powers of this diagonal matrix D, it's going to be either 1, 1, 0, 0 or 1, -1, 0, 0, depending upon the power, whether it's odd or even. And if you multiply V inverse on the left and V on the right, you will get a form which is shown here on your slide, that P raised to power k through this diagonalization process is equal to this 4 by 4 matrix, where all rows are same and they are 1/6, 1/3, 1/3 and 1/6, plus -1 raised to power k, and then this matrix which has the same form but some entries are negative and some entries are positive. This format was obtained by using the higher powers of D, which had two entries. The top left entry was always 1, and if we use that entry with V inverse and V, we get this matrix. And the entry at 2, 2 was -1 raised to power 1. And that is being used here. So n is replaced with k, and this is what you get from V inverse times that second entry times V. So at any index k, the kth power of P is going to be sum of these matrices. Actually, it's going to be sum if the k is even, and it's going to be difference between first and second if k is odd. So this is the simplified version of the high powers of one-step transition probability matrix, and it is clearly shown that for this case the result is going to switch between sum of the two and difference of two. For even sampling instances, you will get P raised to power k, which is sum of these two matrices, and for odd sampling instances you will get a difference of two. And if that is the long-term asymptotic behavior of Pk, then you can start with any probability distribution, and your distribution at sampling instance k and k plus 1 and then k plus 2 and k plus 3 is going to switch between the two probability distribution. So this simple Markov chain representing a random walk on 4 states with perfect reflection has a periodic long-term behavior where the probability distribution, the asymptotic long-term probability distribution, switches between two probability distributions depending upon the sampling instance being odd or even. Now let's have a look at our last example, the example of that person who tries to go on Hajj and passes through different states, and that Markov chain has 8 states, and we have already seen that it has a periodicity of 3. Let's have a look at the model of that Markov chain. Again, you can see that model on your screen. So in this Markov chain, there is a periodicity of 3, and you will find that there are 3 eigenvalues of the one-step transition probability matrix with magnitude of 1. And this is a recurrent Markov chain with a periodicity of 3. Hence, long-term stationary probability distribution is going to switch. It's going to circulate between 3 probability distributions. I'm not going to perform the actual eigenanalysis for this 8 by 8 matrix for this Markov chain because it will be very difficult for you to see an 8 by 8 matrix on your television screen because of the limited resolution of ordinary televisions. We can wait till HD TVs with 1080p resolution are everywhere before we can hope to show you an 8 by 8 matrix and be able to expect that you see all the values. But believe me, if you perform the eigenanalysis for this Markov chain and its one-step transition probability matrix, you will get 3 eigenvalues with magnitude of 1, and when you take its diagonalized version, you will have 3 eigenvectors corresponding to those 3 eigenvalues. And if you take higher and higher powers of that diagonal matrix representing all the eigenvalues, then there will be 3 entries which will be non-zero, and they will switch between respective values. One entry will remain same, the top left one with eigenvalue 1, and the 2 entries with complex valued eigenvalues which represent 2 other cube roots of unity, they will circulate between 3 values, and you will have a long-term n-step transition probability matrix which is going to be sum of one constant matrix and then 2 matrices with those complex numbers raised to power k. And you are going to switch or circulate between 3 long-term converging destinations of the sequence of n-step transition probability matrices. What I am going to perform is the eigenanalysis of a modified version of random walk. In the example that was shown to you a couple of minutes ago, the reflection was perfect. That is, if the random variable assumed a value which was at the end, either right or left, at the end of the chain, the next value was with probability 1 to be the next neighboring value. So if at sampling instance n, the random variable assumes a value of 3, then at n plus 1, it is definitely going to be 2 with probability 1. So reflection was perfect. Similarly, there was a perfect reflection from 0 to 1. I'm going to change that. I'm going to assume that on state 3, the reflection is not perfect. There is a certain small probability that if the random variable has reached state 3, the next transition will find it there again at state 3. We are going to assume this event to have a very small probability. Let's assume 0.01. So with 99% probability, random variable will take value 2 after it has taken a value 3, and with 1% probability, it's going to take the same value again on the next transition of this Markov chain. Let's have a look at this modified Markov chain, its model, its one-step transition probability matrix, and other matrices that are obtained if we do its eigenanalysis. You can see the results on your screen, which shows that from state 3, there is a probability of 10 raised to power minus 2 or 0.01 of returning to that state again. And there is a probability of 0.99 of getting reflected and moving to state 2. The difference in one-step transition probability matrix for this modified Markov chain is in this 4th row representing the 3rd state, the last state. And here you see that there is a probability of 10 raised to power minus 2 in 4,4 location representing probability of returning to the same state in the next transition. and going to the previous state, it happens with a 99% probability. So I'm just going to show you the matrix D. Matrix D is the matrix of all the eigenvalues. So if you take this one-step transition probability matrix and perform its eigen analysis, you get eigenvalues of 1 minus 0.9967 plus 0.5017 and minus 0.495. You know how to take higher powers of this P through this diagonalization process. You take higher powers of this D and then you multiply it with V inverse on the left and V on the right. You can clearly see that if you take very high powers of this diagonal matrix D, this 1 is going to remain 1, but this second number, which is close to 1 but certainly less, its magnitude is close to positive 1 but certainly less, it's also going to become 0 but slowly. And these two numbers, 0.5017 and minus 0.495, they are going to quickly converge to 0. So eventually you are going to have a matrix with only one entry being non-zero, which is 1 at 1, 1 location, which implies that this modified Markov chain with imperfect reflection has a unique long-term stationary probability distribution. I hope you have made this interesting observation that by slightly modifying a simple Markov chain, you have changed its long-term behavior. Previously, with perfect reflection, this Markov chain had a periodicity of 2. The long-term probability distribution switched between two values. But by making this reflection imperfect on one end, we have transformed this recurrent chain into an aperiodic recurrent chain which has a unique long-term stationary probability distribution. Furthermore, you can find this long-term stationary probability distribution from this eigenanalysis. You have D, which is 1, then a number negative slightly less than 1, and two numbers with magnitudes closer to 0.5. When you take very high power of this diagonal matrix D, you eventually get 1, 0, 0, 0. You have a correspondingly V, a matrix of 4 eigenvectors that we obtain through eigenanalysis. You take that V, take it inverse, and then find V inverse time D raised to power very high number n, and then V. You know that this D raised to power very high number is going to give you 1 and then everywhere 0. 1 at location 1, 1 and everywhere else 0. So it's easy to take V inverse times this matrix and then times V, and you got your long-term P raised to power infinity, which has all rows same, and these rows have entries which I have found out, and they are 0.1664, 0.3328, 0.3328 and 0.1681. So this modified Markov chain has indeed a stationary long-term unique probability distribution with middle entries almost twice the end entries, and end entries are not the same. One is slightly less, other is slightly more. Let's modify this Markov chain a little more and make this imperfect reflection closer to perfect one. That is, probability of that Markov chain going from state 3 to state 3 in one step is 0.0001, that is 10 raised to power minus 4, and probability of going from 3 back to state 2 is 0.9999. With this almost perfect reflection, you will get a one-step transition probability matrix. You will perform eigenanalysis of that, and what you will get is again 4 eigenvalues, and these eigenvalues will be 1 minus 0.99996667, very close to -1, that is magnitude very close to 1, and other two numbers will be very close to 0.5 and -0.5. One will be slightly more than 0.5 and other will be slightly less than 0.5. So you will have these four eigenvalues in the diagonal in matrix D. And if you take very high powers of this matrix D, eventually you are again going to get 1, 0, 0, 0 in the diagonal. Even though you have to take very high powers of this diagonal matrix so that this number with a lot of nines after decimal converges to a value which is 0. But if you eventually take this high power of D with 1, 0, 0, 0 and take V inverse on the left, V on the right, and find very high powers of P, you will get a stationary distribution with all four rows being the same, and these rows will have values which are very interesting to see. I want you to complete this eigenanalysis, complete the solution of this imperfect reflection Markov chain, and find the unique long-term stationary distribution and see why, even with just a little bit imperfection, even with a probability of 0.0001 of moving from state 3 to state 3 in one step, makes this Markov chain have a unique long-term stationary probability distribution. I hope you will be able to complete this problem using MATLAB. In today's lecture, we continued with our eigenvalue, eigenvector analysis of one-step transition probability matrices of simple, small, finite state Markov chains. And we learned the role of eigenvalues which are 1 and eigenvalues which have magnitude less than 1. If there were more than one eigenvalues with magnitude 1, we found that that Markov chain exhibits a periodic long-term behavior. And if there was only one eigenvalue with magnitude equal to 1, then that Markov chain had a unique long-term stationary probability distribution, and that was obtained through eigenanalysis followed by the higher powers of diagonal matrix D, which is an easier and more tractable operation than taking the high powers of original one-step transition probability matrix P. The last example was very interesting, where a periodic Markov chain with periodicity of 2 was changed into an aperiodic Markov chain by introducing a very small imperfection, a very small probability of returning from state 3 to state 3. Why this behavior was observed, it will be covered in the next lecture, where we will talk about bipartite and tripartite graphs. Till then, I wish you the best. Thank you. Khuda Hafiz.